Correct. So, so the optimizer goes through this process. Any SQL or data frame first gets converted to unresolved logical plan. Then via cataloging, it gets converted into logical plan, and we'll now go into details how does this happen. From there, optimized logical plan via logical optimization, then physical plan via physical planning. There are many physical plans which get created. Out of this, one physical plan gets selected based on certain cost model, and we'll go into details of that. For that physical plan, RDD is generated. The tree is the main data type. The optimizer, all of these things are happening via optimizers, and optimizer runs rules in each of these steps, and we'll go into the type of rules for each of these separately. Now, for rules to run, it takes everything, it takes a tree as an input. Some rules are running here, some rules are running here, some rules are running here. So at every place, a tree is an input and another tree is an output. So what happens during that time? So consider this tree, a tree has node has type or 0 or more children. Now this tree you can represent as this. So you have a literal which has constant value. You have attribute, a node called attribute, which has which is type string, and then you add node, which is which has left and which is right. So it's basically sum of two expressions. If you have to represent this tree, x plus 1 plus 2, you will using these expressions, you will express add an attribute on the left hand side is x, and on the right hand side, this is another one which you again sorry, which you again have an add node, and then you're adding literal 1 and literal 2. Now the rule, the only purpose of rule is to manipulate the trees, to optimize the tree. So it takes one tree as an input, applies the rules, and outputs another tree. Now how does it apply the rule? It applies the rule based on the pattern matching rules. So we'll take one example. So in this case, this is a scalar syntax. So when you say case, basically immediately after the case is a pattern. So, and this is a transform. This is a transform method, and we'll go into some code. If you have to write your own transform method, does Spark allow you to do that? If it does allow, then how you can write it? So here it finds this pattern, and this pattern is basically there's a add node which is summing up two constants, two literals. So instead of having a 3-node tree, you can have only 1-node tree and say replace everything with 1 node which is literal, which is a combination, which is sum of these two constants. So case keyword is matches the pattern. This is what we said, and here it will match add node which has two literals as subnodes, and outputs a new node which is sum of subnodes. So now if you see x plus 1 plus 2, right here, whatever example we discussed, it will result in x plus 3. So these two nodes will go away from here and gets converted into one constant, which is 3. Okay. So now pattern matching functions. So you see this an example which we saw. These are transform functions. So in the transform method only you are calling this, right? These functions. This implementation is inside the transform method. And these are partial functions. So what are the partial functions? They don't get applied over the whole tree. They get applied only on the part of the tree which is matching that pattern. So that's why we call those partial functions. Catalyst called transfer method to apply these rules, and I will show in graphical way later how does that work. And one important thing is here we discussed one transform which has only one rule, but you can have as many rules as you want. Just example of some other rules. So this rule we already discussed. If you have two literals getting added, then why you want Spark to go navigate this tree, the two literals, just sum this up and put it here, right? So that way you are reducing the tree size also. Another way is if you have some literal, if you have some add node on the left hand side is some value, and on the right hand side is literal 0, then just convert that into left hand only. You can ignore this side, this node. Same is the case vice versa. On the left hand side you have literal on the add node, and left hand side of add node is literal, right hand side is right. Just replace everything with right only, right? Because adding anything to 0 doesn't change anything. So idea is to show you that a transform functions can have many rules. Uh, now what happens is a catalyst groups those rules. So again, I'm just reiterating. Let me go back to the previous. Here it is. So catalyst group, there are rules here, there are rules here, there are rules here. Whatever rules are getting applied here, for example, those are grouped into batches, right? So these are grouped in batches, and at each place here, it runs those rules in batch one after another, correct? Runs each batch on the tree until, and how does it know? Like there are, let's say there are many batches, there are many rules, convert into number of batches. So start with the one batch and start applying the rules, and it keeps applying those rules again and again and again till the tree stops transforming. And I have an example of that when we go into details. Why does it need to apply again till stops transforming? I know what is the need for that. I will discuss that later. But here idea is that you understand that you have the rules into the batches, and it applies those batches one after another, and within one batch it keeps applying those rules until tree stops changing. Why does it do that? So one transformation in the tree might result in a subtree which can be transformed again based upon the rule. So that's the reason. Let's say if you have added, let's say there is a little here also, so if you have little here, you have little here, you have added, and so first transformation you do is this, and you convert into one rule. The batch has one rule, so one iteration will convert into this and put one literal here. Then it applies the same rule here and say there's a literal here, there's a literal here. Then I don't need these two nodes. I'll just put the literal here. So second iteration happens. Then it tries to apply the same thing again. It finds there's no match, so it keeps the tree same, and then it just move on to the next batch. So, so Spark executor flow, so I just repetition of what I just said. Catalyst tree transformation happens in 4 phases. Analyzing this, focus on this, analyzing a logical plan to resolve references. So unresolved to logical by analysis. A logical plan optimization, physical planning, code generation to compile parts of the query into Java bytecode. So that's what it does. Now going to each of these. Analysis. A relation either from SQL or a data frame is given to Spark. Right? It may contain unresolved attributes. So this is what I said earlier also, that you have select column from table 1. So here Spark does not know whether column is valid column or not, whether this column exists in this table or not. Spark does not know. So it applies the rules, and this will tell if will validate this column exists in the table, and it will put into the logical plan. And how does it do that? It has a catalog. So from this catalog, it references, like if you deal with Hive, then Spark has integration in Hive. The data from on this catalog will come from Hive. Otherwise, Spark, whatever your data source is, it just refers to that, and tries to validate this via catalog and convert into logical plan. Second one, the logical optimization. So this optimization is rule based and cost based. Now, what is rule based? Rule based, you have certain fixed rules. One is predicate push down, projection pruning. I don't know whether all of you know predicate push down or not. I have an graphical example of that, but idea of predicate push down is simple. Let's say to help you explain better, let's say you are creating a data frame by querying a MySQL table, and that SQL table has millions of records or billions of records. But your query is that select from that table where the either in your data frame filter condition or where clause in your SQL, wherever you put, and you say where column 1 value is greater than 10,000. So now the table might have 100 million records, but when you apply this condition where column value is greater than 10,000, it returns, let's say 1 lakh record out of 100 million. So what Spark logical optimization will try to do is, it will try to push down this predicate. Predicate is nothing but a where condition. So trying to push that where condition on the database server itself, on the MySQL itself. What it will try to do is, it will try to evaluate out of 100 million records, come up with 1 lakh records on the MySQL server, and return and pass that 1 lakh records over the network to the Spark layer. If it does not do that, then your all 100 millions will be passed from MySQL to the Spark layer. Then on the Spark layer, you will be out of 100 millions, you will be applying filter and figuring and getting only 1 lakh out of that. So that is not performant. So performant is push it down on the DB server, push down the where condition on the DB server or whatever your data source is, and get it evaluated there, and then get only the needed. So that helps in the improvement a lot. Now, how do you check that? I think we discussed that during our session on the explain on the plan session. Is that you put explain in the explain, you can see predicate push down will be there. If it is blank, that means predicate push down is not happening. So if you are querying a DBMS or any table where you want predicate push down to happen and your plan is not showing it, then there is something wrong. Then you have to do something in your code, maybe put the proper filter condition or some syntax might be wrong in your code, fix that and print the plan again. You will see predicate push down is equal to true, and then it will tell you on what basis it's doing the predicate push down. Projection pruning. Projection pruning is, let's say you have 100 columns in a table or in an entity in a data source, and you need only 10 columns. So your select query is select table 1, select column 1, column 2 from this table where condition is this. Condition where condition is predicate push down, select column 1, column 2 is projection pruning. So your table might have 100 columns, but you're selecting only 2 columns. So it will prune or rest of the 98 columns and give you only 2 columns. So there are many rule-based examples. I'm just giving 2, but you can read the Spark documentation of Spark code and figure out there can be many more such examples, and you can build your own rule-based optimizer optimizer rule, and I'll talk about it towards the end. The second type of optimization is cost-based optimization. Cost-based optimization, this is what it is, right? It creates many physical plan and compared for the cost. At this moment, the cost is only the number of rows. So once it finds, and what it does is, at this moment it used only for joins. If it finds that there is, by applying this predicate push down, there are 2 tables you are joining in your data frame, for example, right? Data frame is result of 2 tables, joining table 1, table 2, or in your SQL query you are joining table 1, table 2. So what it will try to do is, it will try to optimize this. It will try to put all the predicate push down, projection pruning, and all of this, and try to figure out now out of these 2 tables, which one is smaller table, and is that table that small that it can be put into the, it can be broadcasted and broadcast join can happen. So that's what physical planning it will do. So physical planning is focused only for joins at the moment, and that too only for making sure whether broadcast join can happen or not. And I have an example for that also later. Now there's another thing which is happening. If you're dealing with Hive, there is a command in Hive where the command looks like something: analyze table and give the table name and compute statistics. So if you give analyze table and in that give the table name and mention compute statistics, it will give you some idea what that total number of rows in the table are, what is the min value of integer column, what is the max value of integer column, some metadata it will give you. Another implementation of this physical planning optimization is that it will refer that if you're dealing with Hive, it will refer that and try to come up with the cost model based on the number of rows and the filter and everything, and try to arrive the entity which might be smaller. So it uses that also here. So these are the 2 things, rule-based and cost-based. A physical planning, which is this. We discussed this cost-based optimization, discussed in last slide too. So many physical plans are created, right? It will try to create many physical plans, and based upon the cost, which is only join at this moment, it will try to see out of this physical plan which physical plans suit better. Like, to give an example, one physical plan could be I don't know, maybe predicate push down is not happening, created that and figure out cost is high, versus another physical plan which has predicate push down happening and cost is less because number of rows are less, and it found out that is better because with that physical plan it can push one data into the broadcast and do the broadcast join. So that's how it happens. Physical planning also performs rule-based optimization, which I already discussed, right? One unique example is pushing filter. Let's say you have in your data frame, you are saying data frame dot map then dot filter. So it will figure out that you have dot map and then have dot filter after that. So why not apply that filter inside the map function itself? Because whatever you are filtering on, that column is available in the map also. So it will apply, you have 1 million record and you are applying a map function over those 1 million records. So map function will go over 1 million records. After that, you are applying a filter and saying where column 1 value is greater than 1000. So what this will do is it will, put, because it's generating the bytecode for you anyway. So it will put that, condition where column value is greater than 1000 inside your map function itself, so that your map function also get reduced and you avoid one extra step also. Of course, it also does the predicate push down to DB, which we already discussed, that if you are reading from MySQL or RDBMS or some DB which is allowing the where condition to be evaluated on the DB server, it makes sure it gets pushed there, and then you get the right data and you get the data in an optimized way. So that's how physical planning works. The code generation. So code generation is basically, it just generates a code. And generates a code, it has an optimization built it. That code gets generated in a way that it just speeds up the execution. And this code is in nothing but an RDD. You are dealing with data frame, data set, or whatever, all of this. It does a hell lot of optimization in all of these steps. Ultimately, it generates an RDD and it executes. These are some of the links. I have referred those links to create this material. So you can, and these are very exhaustive links. I mean, I think this is half an hour video. This is one blog, this is another video. Go through this. You might get, more insight into how optimizer works. Now we'll go into one example. So I think we covered half of it already. So we'll go into one example. Let's say you have this query, select sum from select T1. There are two tables we are dealing with, table 1 and table 2, and these are getting joined. So what we are doing is we're selecting table1.id 1 plus 2 plus table1.value as v, and then we're getting sum of v, and we are applying this where condition. Don't try to interpret this. Only thing you understand from this is that there are two tables, and these two tables, we are joining these two tables, and we are selecting few columns from these tables based on certain where condition. Correct? And so there's a tree which will be created. So there's an expression, there are attributes, correct? So what is an expression? What's an expression? Expression is basically represents a new value, compute based on input value, compute based upon the input value. So this is an expression, for example, 1 plus 2 plus T1 value. So an attribute is a column of a data set like T1.id, T1.value, and things like this. This is an attribute. So these are expressions and attributes. Now, the optimized query plan, like we discussed, the logical plan, then optimized logical plan, and all sorts of things. So this is a plan. So what it does, it will try to create a tree structure out of it, right? So select, you have sum, right? So it becomes an aggregate, which represents sum of v. Then you are projecting that you are getting only T1.id and 1 plus 2 plus whatever this will be. So this is a projection. Then you are applying filter, right? This where condition T1.id is equal to T2.id. These are the filters. Then you're doing a join, right? The table 1 and table 2. So this is how it will construct the tree structure in the beginning. Then what is going to do is, in the logical plan, it's going to create, of course, we discussed, right? It will refer the catalog, make sure the attributes are valid, in the query whatever given is all valid. Then ultimately it comes with a logical plan. So a logical plan describes the computation on the data set without defining how to do the computation. Take this example. You're just taking aggregate. You're not, and we'll see in the other plan, but is this how this aggregate is created. So logical plan does not tell, it just tell what you want to do without defining how you want to do. Join, what type, how the join should happen. I think we have defined here in the physical plan, but logical plan will just mention about the join. And so this is the logical plan, correct? And then physical plan will do how to do those things. If you have a aggregate, then what type of aggregate? This is a hash aggregate. If you join, what type of aggregate? Is a sort mod join. Here I am reading the files. So what type of file reading is happening? Spark join is happening. So if you would have seen in our example where we went to the Spark UI, You would see in the UI, you can see the Parquet scan is happening in the graphical user interface, and you can see how many files it read. And you can see all of that on the last tab, I think the SQL tab on your UI. So this will appear there as well. And physical plan is the one which is executable. Transformations. So we'll go into details. I think more or less for our understanding, if you have understood till this much, this is more than enough. Now I'll be double clicking on this and going into details of this. So transformation without change. There are two types of transformations. So one type of transformations are with do not change the tree type. So you have expression and expression, logical plan as a logical plan, physical plan as a physical plan. Other transformation is transforming one tree type to another tree type. For example, logical plan to physical plan you convert, right, by applying the physical planning we discussed a few slides back. Now this is a repetition, as I said. So take this example. A function associated with every tree used to implement a single rule. So we discussed the rules, right? One rule, and then there are batches which will have set of rules. So let's take this example. You have this tree 1 plus 2 plus t1 dot value, right? So this is 1 plus 2 is a literal here. It's going to add node, and then this add and this t1 dot value gets added here. So what it will do, one rule will do is 1 plus 2, it becomes 3. So all these 3 nodes get converted into 1. So this 1, 2, 3, 4, 5 node tree gets converted into 3 node tree, right? This is one rule, which is example of simulation of one rule which gets executed. And now a transform is defined as a partial function. So we discussed that, correct? And partial function and function that is defined for a subset of its possible arguments. Like in this case, a tree, we are applying a pattern on that tree, and whatever pattern is matching, where this transformation is happening over that. So that's why it's called a partial function, correct? So this is we discussed that this case statement. The case statement determines if the partial function is defined for the given input. Like you have a tree given to it, it just validates if this is matching on that or not. This highlighted in the green is match. A tree has that pattern or not, right? So that's what it is saying. Now you can combine multiple rules also. We discussed in one transform you can have multiple rules as well. So one is predicate pushed on. You see there's a filter, right? Instead of applying filter on t1 dot, let's say t2 dot id is greater than 50,000, it pushes that filter here. And so now, because from the database itself, you're getting less records and your join will be better, correct? Instead of getting all the joins and then doing the filter, it's less performant, whereas you are filtering less records and doing the join, correct? And then you will see here, you are projecting also in the column pruning. So column pruning we did not discuss. And by the way, another thing which I forgot to tell you is the predicate push down is happening, right? So filter is getting pushed down, predicate push down is happening, and this is projection. You are doing column pruning. We discussed that already, right? These tables might have many columns, but in your query you saw that the select some query, you need only few columns. So t1.id, t1.value here, and t2.id. Only 2 columns here and 1 column here. So why to get all the columns in your, get the data for all the columns here? So it will do, column pruning. So it will do projection. How it does column pruning is by using projection. And projection tells that, you select only these columns and select only this column from this relation. Now we'll discuss about transforming into, this is just a simulation if you're transforming into the same type of tree, right? And we discussed the rules are applied in form of batches. So so batch, a rule execute transform a tree to another same type by applying many rules defined in batches. So it in another slide here. So in one batch, you will keep applying these rules, and these rules will keep right. You see this rule 1, then rule 2, then another rules, then go back to rule 1, then rule 2, then rule 10 goes back. Where it stops is that when you reach a fixed point. What is that fixed point? A fixed point is where the tree stops transforming. When tree does not transform anymore, that's where you stop the stop these rules, then move on to another batch and do the same thing with that batch. And each of these is getting executed in your analysis phase, in your optimization phase, in your physical planning phase. So each of these steps, each of these the batches which are the batches of rules which are getting executed in analysis phase, there are different batches of rules which are getting executed in your optimization phase, and same with physical planning phase, right? So once rule executions, a rule execute transform a tree to another tree by, okay, this is the same thing. Every rule is implemented based on the transform, right? So what you can do is you can have the when you implement the rule in your transform method, you can tell that you apply rule only once and you don't have to repeat. That is also possible. So instead of going through this loop again and again and again, you can always say the fixed point is here. Till the fixed point is reached, you just keep applying. And here you can say, for particular batch, you can say you apply it only once. Don't go into these batches. So that's also possible. And we'll see the Spark API, which you can use if you have your own rules, if you want to create your own rules and be able to specify these configurations. How does it convert from logical plan to physical plan? So logical to physical plan conversion happens by applying set of strategies. So in below example, logical projection is being converted to physical projections using some strategy, right? So this is extraction strategy. And then logical filter is being converted into physical filter. When more than one strategy needed for conversion, plan later is used. You see, this is an object, this is a scalar code, right? And you're having one strategy. And this strategy, you are doing something, right? You are projecting, you are filtering. And after that, you want to apply more strategy, then you can say plan later. So in the tree, whatever in your strategy set of strategies, whatever is the next strategy, it will execute that. Putting it all together. So you have this data frame, SQL, and data sets. Now data set, I was not there in the first slide, but here data set is also there. It goes to query plan, unresolved, logical, optimized, physical. It does all of that. Ultimately, RDD comes out. So this is all put together. We'll go into before I go further. Any questions so far? Okay. So now this you don't need to know the details, but this is what we already discussed, and I'm just copy pasting from the Databricks documentation, and here just trying to explain the same thing by repeating. So the steps in analysis, it transforms an unresolved logical plan to a resolved logical plan, and it uses a catalog to find where data set and columns are coming from and the types of columns. The logical optimization transforms a resolved logical plan to an optimized logical plan, and that is we discuss so many optimizations happening, the rule based and the cost based and all those things. The physical planning, strategies plus rule executor, it does both of these things. It transforms an optimized logical plan to physical plan, and rule executor is used to adjust the physical plan to make it ready for the execution. Yeah, I think code generation, I'll leave it for time being. We know how, it uses some, it uses some scalar library for code generation. So it just read it into RDD. So I'll skip this also. This is what we'll discuss, extension points. If you have to write your own rule, how you can do that. And these are the videos. These are PPTs and the video. You can go through this if you want to know how to write your own rule. You want to add your custom code to the Spark Catalyst pipeline. So how to do that? So same diagram in a different view, in a different coloring and in a different way. Your parser, unresolved logical plan, analyzer. And so here, whatever was analyzer was here, I put it as here, and whatever was here, I put it here. So unresolved logical plan goes to analyzer. Some rules get applied. It converts into the analyzed logical plan. Then it goes to optimizer. Some rules are applied. It converts into optimized logical plan. Then it goes to Spark planner, Spark strategies, and the rules are applied. Then it gets converted into the physical plan. Right? Now, supported customization. So same thing here. You just take the same thing. In each of these, in your parser, analyzer, now what you have to know is, now these are the verbs. These are actions. Like these are the things which are doing some actions. So parser is doing parsing, analyzer is doing analysis, optimizer is doing optimization, Spark planner is doing Spark planning. So you can have your own extension points. You can have your custom parser, you can have custom and rules for analyzer, custom rules for optimizer. custom Spark strategies. How to do this? So they have come up with an extension API at very high level. There's a new Spark session extension class. So this class is used. It has methods to pass the customizations. It holds a customization. And when you are creating a Spark session in the Spark session builder, Spark session.builder, we have been using this for quite some time. In Spark session builder, there's a method called with extensions. So in this with extension, you would have implemented your new class which has this Spark session with extension. It should extend the Spark session with extension, and whatever your implementation is, you can pass that class in with extension method while doing the Spark session.builder, while using Spark session.builder. Some examples how it happens. So in your parser, when there are inject methods, these are extension hooks. So injection function used to inject a function available in the next Spark release. Right now you have these implementation. You have inject parser, you have inject rule. So I think they're coming with some inject function. So that will be happening in the next Spark release. But in your parser, you can use inject parser to have your own parser work on the plan to pass pass the inputs data frame or SQL. You can have for analyzer. You can inject resolution rules. You can inject check rules. You can inject post hoc resolution rules. I don't know what HOC means. Post hoc resolution rules. You can inject your optimization rules and all of these things. Inject function is in this Jira ticket. You can go and check this. Here you can inject your planner strategies. So once you have this, once you use this class, you'll get availability to all of this. You can override and do whatever you want. And now, so that's about it. I think for your customization, you can use this class and override any of these methods and build your own logic based on your business requirement. You can come up with what type of data you're getting, what type of business processing you do. If you are thinking some business processing is constant, which you do no matter what, maybe put that it doesn't change based on the input of data or something. Maybe put that in your optimizer. Possibly from 2 node you can convert into 1 node, something like this you can always do. So this is about your custom customization of your optimizer, analyzer, or planner, or everything. Now what we'll do is we'll take one example how cost-based optimization work. We talked about cost-based optimization 2 times in this session. So we'll take an example. Now this is used while joining 2 tables. So now when you're joining tables, you have build cell table and probe side table. Smaller table is chosen as build cell table, right? Build side to have hash table. We'll take 2 examples. Let's say you have table 1 and table 2. This is table 1 and this is table 2. Table 1 is 500 GB in size. Table 2 is 20 GB in size, correct? And table 1 has 5 billion records. This is 100 billion records, something like this. And now if you don't do any planning, and you have filter on the, one important thing is you have filter on the 500 GB side. Now after filter, this 5 billion records get converted into 1 million records, and this 500 GB gets converted into 100 MB. If you don't do any optimization, by default, Spark will think that this is the smaller table because this is 5 billion and this is 100 million. It will try to make this as your build set table and try to see if this can fit into the this can be used as a broadcast variable, and broadcast join can happen over this. But and you can sorry, and then I think that's it. But if you apply the cost-based optimization, then Spark and Spark will filter this out, and then consider this table. Whatever is the output of this table is it will apply the predicate push down on the source. And once you apply predicate push on the source, out of 5 billion, you're getting only 1 million. And comparing between 1 million and 100 million, the cost-based optimizer will figure out this is a smaller table, and this smaller table can go into the be sent as a broadcast variable, and broadcast join can happen over this. So this is the advantage of cost-based optimizer, because it just calculates the cost. What is cost in Spark terminology, Spark automation terminology? Cost is not dollar or rupee or something. It's just the number of records. And, so that's what cost is for Spark optimization. I think that's about it.
Sandeep, one question.
Let me pause the recording.